Inverse Kinematics. Nowadays, it is probably one of the most useful tools for animation out there. IK is used basically everywhere. It greatly simplifies the process of creating keyframe animations, and more often than not is an absolutely essential part of procedural animation. But how does it work? I mean, if you watch a Blender tutorial, they will teach you how to set up Inverse Kinematics. You click a few buttons and get this. Pretty cool, right? It's very obvious how useful this can be, but what is happening behind the scenes? What algorithms are used there, and why is it called Inverse Kinematics? Well, I guess it's time to find out. First, let's try to understand the problem that IK is solving. Imagine we have a limb, basically a chain of segments which can be rotated relative to each other. Each segment has a constant length which is known to us. We also know the origin location, the point to which the first segment of the chain is attached. On the opposite side, we have this point. Let's call it the end effector. If we know relative rotations of all segments, we can calculate the location of the end effector. This problem is called forward kinematics. But let's inverse the problem. Let's say we already know the end effector location, so the relative rotations of all segments is what we want to calculate. And now this is called inverse kinematics. Yoo-hoo! It's finally clear why it's called inverse kinematics! Fun fact, this problem originates from robotics. And, well, it's quite obvious when you look at robots like this. But over time, it looks like people have found great use for such algorithms in animation and even later in game development. Yeah, that's how we get here. Alright, now the problem has been established. But how do we solve it? Well, there is a whole spectrum of algorithms, which can be divided into three general categories. Analytical algorithms are approaches based entirely on pure mathematics. Before using them, you have to determine concrete formulas for the given limb, so later the program can just put numbers in there. This is computationally fast, but can be a real hassle to set up. Iterative, or as mathematicians like to call them, numeric algorithms, take a different route. Instead of finding concrete solutions by solving the problem mathematically, they perform a series of similar calculations over and over again, thus slowly approaching the solution of the problem, while never really reaching it. In mathematics, this is called approximation. Such algorithms are very flexible. They can work on pretty much any limb with no prior setup. But as a trade-off, they are relatively slow. And lastly, we have more complex algorithms that either try to combine the first two methods in some ways or use something entirely different, like machine learning, for example. For the sake of simplicity, and to post this video before the previous one gets 3 months old, we are going to only have a look at just one iterative algorithm.
But when we figure out how it works, we'll apply some real black magic to it to make it really powerful.
The algorithm we're going to be looking at is called FABRIK, Forward and Backward Reaching Inverse Kinematics. This is quite possibly the simplest IK algorithm one can come up with, so let's not waste too much time on explanations. We start by finding the location of the last limb segment relative to the end effector. Then we align the last segment's rotation to face the end effector and modify its location, while maintaining the direction from the end effector and only adjusting the distance, so it matches the length of the segment. This is quite similar to polar coordinates, if you know what those are. When that's done, we continue performing similar calculations on other limb segments, going from the end effector to the origin. The only difference here is that instead of the end effector's location, we use the location of the previously modified segment. This is called forward reaching pass. Once we have processed all of the segments this way, we set the location of the first segment to match the origin. Then we turn around and start going in the opposite direction, Again, we find the location of the next segment relative to the current one, and shift it along the radius vector, so the distance exactly matches the length of the current segment. When the backward pass is complete, we say we have performed a whole iteration. We keep repeating these iterations until we either reach the maximum number of them, or the limb happens to match the necessary origin and end effect locations with a good enough precision. Congratulations! You now know how FABRIK algorithm works. But the raw version of it isn't very powerful. It is fast for an iterative algorithm, but you have basically zero control over how the limb bends. This is a big problem. The standard way of controlling the limb's shape is using angle constraints. Basically, you do not allow your segments to rotate beyond certain values. Even though it is generally a really good idea to have something like this in place, as it basically guarantees that the resulting solution will make sense, I personally don't find it very pleasant to use in game development scenarios. That's not to mention that I have kind of maybe not really implemented it. I tried for the video, but abandoned the idea due to time constraints. At least that's the official theory. But all of that is of no matter now. As from the very beginning, my eyes were already peeled to a different approach. The more interesting and artistically flexible way to control limb's shape. Pole targets. If you have used IK in Blender, you're likely already familiar with the concept. But in essence, this is how it works. We introduce a new point in space, which, generally speaking, is completely independent from the limb. This point defines the bending direction. So, if you, for example, animated a human leg, pole target would mark the direction of the knee. There are versions of IK algorithms that natively support pole targets. But for some reason, past me decided to stick with FABRIK and add pole targets to it manually. Which, well, I actually did. It was, in reality, not that hard. The idea here originates from a rather simple observation of how FABRIK works. It does not override the current shape of the limb, but rather modifies it to approach the conditions. This means that limb's final shape somewhat significantly depends on the initial shape. So, if we, let's say, provide an initial state that matches the pole targets, but does not solve the IK problem, theoretically, the resulting solution should significantly depend on the pole target configuration. So, what I ended up doing was this. Before each run of the algorithm, I reset the shape of the limb by making each segment face the direction of its pole target. Then I just run the algorithm normally, and everything works fine. Surprisingly. Man, I love iterative algorithms. Anyway, the really cool side of this modification is that if we want to, we can give each segment its own pole target. Unlike in Blender, where you only have one pole target per IK chain, which means that you have to somehow work around it. My method gives us a natural way of animating limbs like this, which is something I really wanted to do. What I also ended up doing was placing these pole targets automatically. Basically, this vector defines the location of the pole target in limb's relative space. X corresponds to the axis going from the origin to the end effector, Z to the up vector, and Y to the cross product of the two previous ones. This gives us a pole target configuration that just works. But my adventures did not end here. You see, IK only finds yaw and pitch angles for each segment. Roll is, generally speaking, pretty random. This, as you can clearly see on your screens, is a big problem. To solve it, I had to use some math. Don't worry, it's not as scary as you might think. Or maybe it is, I don't know. Anyway, here is what's happening here. We have an already positioned limb. Each segment has some random roll rotation, which defines the current segment normal vector. We need to get all of the roll rotations to make sense, which in this case just means that they must be consistent. Because if they are, we will be able to add some correction values to their rotation and get them to look basically any way we want them to. My solution to this problem looks as following. For now, let's look at any limb segment which is not the first one. First, we find two vectors going from the limb's origin. One going to the start of the segment and the other going to its end. Taking a normalized cross product of the two vectors will give us a normal vector of this plane. I call it solution plane. Second, we find a segment vector. It is a vector going from the start of the current limb segment to its end. Then we take a cross product of the segment vector and the solution plane normal, which, depending on circumstances, can give us one of these two vectors. We can turn one into the other just by multiplying it by -1. Both of these vectors can be used as sensible directions for the new segment normal to face. We just need to pick one. To determine which of the two vectors to pick, I decided to define a target direction. A vector going from the limb's origin to the center of the current segment. Now, if the dot product of the target direction and the vector we got on the previous stage is positive, we just keep the vector. And if it is negative, we multiply the vector by -1. This way, we always pick the vector that is most similar to the target direction. Now, when we have determined where we want our segment's normal to face, we just find an angle between the current and the new segment normal vectors, and use that as our new roll. To do that, we can again use dot product in pair with an arc assign. Whew, almost done. The only problem is that, if we try to apply this method to the first segment of the chain, we will utterly fail. Because the two vectors we used to construct our solution plane and the target direction are now the same vector. This case needs some special treatment. The solution is easy though. We just introduce another vector to act as a target direction and as a second vector for solution plane construction. I used one that faces directly upwards. Whew, this was not easy to explain, I want you to know. But now I can show you the result. Look at this beauty, animates like a charm. I say it was worth it. If you're wondering about the performance, in this totally not reliable scientific test of mine, where I just put 256 walkers and made them walk in circles, I, in fact, didn't notice any difference in FPS. But, well, it might be overshadowed by other stuff within every bit of frame rate there is. Alright, this video took quite a while to make. I think I'm not going to give you any promises about the video schedule this time around, as, well, it looks like I'm not very good at keeping them. But in any case, I still had fun working on all of this and hope you enjoyed watching it. While waiting for the next episode, you may hop onto one of my streams where we play cool games and just have a fun time. And I'm going to be seeing you next time. So until then, bye bye.